So this is the lecture for chapters 11 and 12 that we did not have in class due to the technological issues we were having on Monday. So first, let's talk a little bit about what this chapter is about. Chapter 11 is about images from space. And this is an early photograph of a airfield in Russia, the former USSR, taken in 1966. And this came about based on some spy satellite photos taken as part of the Corona project, which started in 1960, which is part of the reason that we established NASA in 1958, was to become more vested in the space race and space travel, and as it would turn out, putting satellites in space for different purposes. The Corona program basically lasted from 1960 up until 1972, and then it stopped. Now, as it says on the slides, that's when the Corona program stopped, not so much the spying. So when we talk about these satellites in space, there's a couple of different things we need to understand, and that is how they function and how they travel. And so, for example, some satellites have geostationary orbits, some have near polar orbits, and some have sun-synchronous orbits. So when we have ones that have a geostationary orbit, it means it rotates at the same speed as the Earth, and so effectively, if you can identify its location in the sky, it stays fixed. So if you have a satellite television receiver, if you're not on cable, and you're using something like Dish Network or DirecTV, that satellite always points to a certain location in the sky, in the horizon, and it turns out that satellite is moving at the exact same speed as the Earth, and so while it's rotating, the Earth's rotating, and so it effectively stays in the same spot. Other satellites travel on a near polar orbit, which means that it roughly rotates from the North Pole to the South Pole, and it typically laps around the Earth several times a day. And then each path covers a certain amount of area, and they call that a swath. All the while, of course, the planet's rotating. And so, for example, with like Landsat 8, it takes about 14 passes around the globe per day, and each one is roughly 185 kilometers wide. And then you have sun-synchronous orbits, which means the path goes over the same location at the same time every day. And this is kind of important because a lot of times when we're looking at multispectral imagery for remote sensing purposes, the amount of energy that is impacting the surface of the Earth would change dramatically if we measured it a couple different hours earlier or later in the day. And so if you want to be able to take data from 1 or 2 days in a row and sort of begin to piece together things, it needs to look at the same location at the same time. So sun synchronous is pretty interesting in that whenever it comes back around to that same location, it will be at the same time of the day as it was with the previous attempt. So here's what that kind of looks like. Here's an example of that north-south sort of orbit that we're talking about, and how the satellites would move around as the planet rotates around on its axis. And as it does this, each path would go down through and cover some more area. Now the thing to remember is these paths don't line up on a day-to-day basis, and you can see here we have the ground track on day 1, and then you see where day 2 comes in, and then day 3, and then day 4, and then day 5, and 6, and 7, and 8. And by the time you get to day 8, you notice that corresponds to the pass that was directly after day 1, and that's kind of the way this whole system works, and that in time you can then cover everything. And we do this with 2 general types of sensors and equipment. One's called a cross-track scanner, and basically sometimes it's called a whisk broom scanner, where the sensor moves left to right and back and forth as the satellite moves along. It hits a rotating mirror that then sends the signal over to some sort of detector to measure whatever it is that it's tracking. Another one is called an long track scanner, sometimes referred to as a push broom scanner, to where you have an array of multiple detectors and a lens that then looks down at a certain area on the ground, and it then takes an image, and then it moves forward and takes another image and another image and another image. Now, having said all that, there are limits to what you can actually collect, and here we have the same location. We use 3 different sensors that are at 3 different resolutions, and you get 3 dramatically different looking images of the same thing. And so you got to remember that when you look at remote sensing data. It's not always going to be super high resolution picture quality things that you can zoom in on. Sometimes it's going to be somewhat coarse. And here's what we mean. Some sensors collect data in 2 bits, some in 4, some in 8. And so 8 bits like a 256 color grayscale image, if you will. And if you look at these images going from left to right, you have a 2-bit radiometric resolution, a 4-bit, and then all the way over to the end at 8-bit. And you can see that there's a lot more variation in terms of light to dark, which means it's potentially more information there that you can collect. Now, these satellites we've been using for a long time, and some had relatively short life expectancies. Others have lasted quite a while. Some are still in the air, but have problems, and some never made it to space. If you look down this list, you'll see Landsat 1, 2, 3, 4, 5. You don't see a 6, but you see a 7 and an 8. If my memory serves me correct, 6 blew up on launch, and so it never made it to space. Now, within each of these satellites, there's a lot of information to be had, and this information comes from the different sensors that are on board. And if you remember a little bit, we talked about how remote sensing, we look at these different bands of electromagnetic energy, and here are some of the different bands that some of these satellites collect. So, for example, some of the Landsat satellites will have the OLI TIRS instrument, and that particular instrument allows it to collect 11 bands, one being a coastal, a blue, a green, a red, a near infrared, a shortwave infrared, a second shortwave infrared, a panchromatic, a Sirius, a thermal, and a second thermal band. Each of these collecting different information that you can use for remote sensing. Then you have the ETM, which is the Enhanced Thematic Mapper Plus, and it collects up to 8 bands of information: blue, green, red, near infrared, shortwave, thermal, a second shortwave, and a panchromatic. The Thematic Mapper, which is sort of an older, more common one: blue, green, red, near infrared, shortwave, thermal, and another shortwave. And then we have the MSS 1, 2, 3, and 4, 5, which are essentially ones that collect 4 bands. One collects green, red, and 2 near infrared bands. So now that we've talked about that, you can imagine these satellites moving around up in space like this Landsat satellite, collecting all kinds of information that we can then use to distinguish and understand what's happening on the surface of the Earth. So here's an example. This is an aerial photo that was collected with Landsat, I believe Landsat 8 from 2014. And this is part of Alaska, and the image on the far left is before, the middle is during, and the one on the right is the one on the right is after a massive forest fire. And you can see how during the fire event and the one in the middle, you get a lot of smoke and things like that show up in the picture. When you get to the one on the right, you can see the scarred earth, the brown, but you can also see that there's some vegetation that remains intact because you still see green within that space. So you've got all these fancy satellites collecting all these images from space, and say you want one. How do you go about finding it? Well, the first thing is you have to know where to ask. And if you think back to those various paths that we talked about, those satellites making around the globe, the path number is one thing and the row number is the other. And so for any one location, you need to know the path and the row for where your target area is at, and then from that you can then collect information from the satellites for that particular path and row. And here's an example of the US GIS Global Visualization Viewer GloVis. They change this thing pretty frequently. It likely doesn't even look like this anymore, but if you go into GloVis, you can request a certain path and a certain band, and it'll show you exactly where that is and what data you're going to get, and then you can look at what satellites are available. And, excuse me, and from that you can then collect whatever information you need. You can use the information from these aerial photos to learn quite a lot. Here we have an aerial photo taken from satellites. I guess it's really a satellite photo of part of the rainforest in Brazil, the Amazon. And then the next image, top right, you see the early input of a new road system and an extensive roads going off to the sides of that. And these roads going off to the side are essentially logging roads. And basically, over time, they go in and they harvest out the forest, and then they have to make longer, more roads and harvest more and more and more. So then you go from the top right to the bottom left, and then from the bottom left to the bottom right, and you can see how the dark green, which was the original Amazon forest, there's so much less of it, and then the lighter green is the less dense new growth that's recurring over the areas where they've already went in and harvested the forest. The next thing we're going to do is spend a little time talking about Chapter 12, where we study the Earth's climate and environment from space. So a couple things I want to talk about when we're talking about climate and remote sensing. Much of the early satellite work revolved around looking at the surface of the Earth, and specifically for more terrestrial sort of things like land use and that kind of thing. Over time, we become more interested in the oceans, more interested in the atmosphere, more interested in weather, more interested in a lot of things. And so we needed to look at ways that we could enhance what we're doing. And so we're going to cover some of this a little bit. And so a couple things I want you to remember as we go through and look at the pictures from this chapter. The EOS is just an acronym for Earth Observing System. And the first one of those that we're going to kind of talk about is the Terra system. And Terra was a joint venture between the US, Canada, and Japan. And it's part of something called the Morning Constellation. And clever bunch of these remote sensing folks are. It's because this group of satellites, they tend to go over the equator all in the morning. And so they call this the Morning Constellation. The remote sensing satellites that tend to go over the equator in the afternoon, guess what they're going to call that? Spoiler alert, I'm not going to tell you until we get to that section. So let's just go over what some of these satellite systems are called, what it actually means, and maybe a little bit about what it does. So the first one is the CERES, the CERES, which is the Cloud and Earth Radiant Energy Systems device. And this is just a sensor that's in a satellite, or the name of a satellite, depending on the different ones. And it was designed for climate study, specifically to study clouds. The next one is the MISR, which is the Multi-Angle Image Spectroradiometer, and this is a group of 9 sensors that is designed to examine the Earth at different angles. And so that multi-angle turns out to be the really important part. By being able to look off to the side at different angles, not just straight down, it allows it to cover the entire planet in about 9 days. MOPIT is the next one we're going to look at. It measures pollution in the troposphere. And MODIS, which is a moderate resolution imaging spectroradiometer. And this is a pretty cool satellite. It collects 40 different, or it produces about 40 different data products. And it does that out of about 36 different bands of electromagnetic radiation information that it collects. And then of course there's ASTER, which is the Advanced Spaceborne Thermal Emissions Reflection Radiometer, and this is primarily looks at thermal and infrared information, but basically it's like having a big thermal and infrared sensor with a zoom lens, so you get better resolution information in these particular wavelength ranges. So here's a nice example of what MODIS data can look like. And here we have, this is some of the stuff from the CERES sensor. And again, remember, this is specifically designed for the study of clouds, and you can see how when you look at this you can get some idea of what's going on. MISR, the multi-angle imaging spectroradiometer, 9 sensors, cover the whole planet in about 9 days, and you can sort of see how you can get so much information with that. MOPIT, again, more environmental stuff. This looks at carbon monoxide concentrations, and you can see how they change from March to September and what would happen differently during that time period. March would be spring in the northern hemisphere, but that would be fall in the southern hemisphere, and the spring in the southern hemisphere would be more towards the September side of things. And so as you get more CO2 production in the sub-Saharan part of Africa, that should correspond to spring vegetation growth, perhaps. I don't know. Here we have some MODIS images, and this particular one looks at fires in a national park in Australia, and you can use this information to see exactly where the fires are because they're red. And then after fires, you can use this to go in and identify burned areas. Here is an example of looking at the Nile River, again using some of the different data that's collected with these various sensors. Right up to and including things like volcanic eruptions. So a few other satellites I wanted to mention and talk about a little bit. One is called Aqua, and this is a satellite system that was designed primarily to monitor the Earth's water cycle. The AMSU-A is an advanced microwave sounding unit, and this entire sensor is primarily there just to monitor temperatures. The HBS is the humidity sounder for Brazil, and that basically monitors the humidity or the relative water content in the atmosphere. AIRS, ARS, is the advanced infrared sounder, and it measures temperature, humidity, and it also has some capacities to tell you some things about clouds as well. AMSR is an advanced microwave scanning radiometer, and this is one that's kind of critical because it was one of the first satellites that allowed us to specifically target and collect information about things like the amount of sea ice, the surface temperature of the sea, and things like wind speed. So here are what some of those things actually look like. This is the AIRS sensor, and this shows us the global temperature. And what we're looking at here is the polar vortex that some of you remember from back in 2014. And you can sort of see how, for whatever reason, the cold Arctic air is being pulled down across much of the eastern half of the U.S. So another satellite system we're going to talk about is ARA, which was another collaboration, this time between NASA. And when I say NASA, well, that's basically, I'm talking about the US, Finland, and the UK. And this series of instruments and satellites were designed basically to measure atmospheric chemistry. And so just like the morning constellation, well, they have the A train, which is the afternoon constellation. And this basically includes the Aqua and the ARA systems, and they've got a bunch of different sensors as well, and I'm not going to go through the specific names of telling you what an HIRDLS is, except to know that that allows us to measure temperature, water vapor, ozone, and trace gases. And then there's the MLS sensor, which is for carbon dioxide and ozone, and the OMI, which measures ozone specifically in the troposphere along with certain components in the UV spectrum. And so you can begin to see how these satellites monitor the kind of things that we assume or believe to be causing changes in our climate, whether we're talking about local short-term changes like where hurricanes and how many will develop, where they're going to track, where we expect landfall, that sort of stuff, or whether we're looking at dramatic, more long-term things like global warming, melting ice caps, decreased sea ice, those sorts of things. It's one thing to say something is or isn't happening, to take a political stance on a scientific issue as to what you want to believe, but data is just that. It's numbers that you collect based on real facts, and what we found with these satellites is that we can measure things like the temperature and see that there are trends of temperatures increasing. We can see that there are trends of glaciers getting smaller. We can see that there are trends of there being less sea ice. We can see that there are trends of elevated levels of CO2 and other things, and how this all corresponds to changing the water cycle, and what that means to sea temperature and global temperature and air temperature. And so, rather than just argue about whether we think something is or is not causing something, we can actually measure things, and the more we know about the conditions, the more apt we are at being able to model what is causing it, or what could be causing it, or how we can, or what we should do or consider to do in order to change that. And so that if we can decide, determine, or otherwise come to agreement that fossil fuel is causing this, then we know that that would be the first logical way to combat climate change. If we come to a conclusion that something else is the dominant factor in causing it, then maybe the elimination of carbon-based fuel systems is not going to be as helpful as what we might think. But at the end of the day, if we don't have hard information to base this on, we're just arguing about speculation. So these satellites are very important. So if we were to look across the sky, just to give you some idea of the different ones and how they would be tracking, and this I believe is the afternoon cluster, and you can see how you start off with some of these different ones, and then they follow behind, whether we're talking about the OCO, the GCOM, the Aqua, the Calypso, the CloudSat, the Parasol, or the Aura, and the different sensors that are on board each one of these, measuring things following one after another on a daily basis. And we can figure out a lot from this. This, some of you may have recalled from a few years ago, is the giant hole in the ozone layer that was being caused by the pollution in the atmosphere with hydrofluorocarbons or chlorofluorocarbons. And so we changed the propellants in our aerosol cans and coolants in our refrigeration units, and we've tried to eliminate the things that cause this depletion of ozone to close up the hole. There are other centers we have as well. So this first one on the top of the list here, it has a lot of stuff very similar to Terra and Aqua, but it's also got some different stuff. Basically, it creates a profile of atmospheric temperature and moisture. Then there's the CRLS, which is really useful as far as climatology for forecasting and creating models. And there's the OMPS, which measures ozone, and the VIRS, which is infrared. And this is kind of important because it can, because of its design and structure, it can measure infrared across the entire Earth twice a day. So that provides a lot of useful information. And some more pictures from satellites. This one looking at chlorophyll, and you can see how those chlorophyll levels change from one area to another, different times of the day, different times of the year. Things like coastlines and cities and shadows. Here we have an example of a shadow from moonlight. So you get a lot of interesting things. You see the clouds. None of this stuff would be possible without satellites. If we were to scan out, if you will, and look at it from a larger perspective, this just gives you some idea of how many satellites we have up there monitoring this sort of stuff. And so there is a tremendous volume of data that's out there for scientists to use and to decipher and to understand. And one of the career fields in GIS is remote sensing. Remote sensing is understanding how these different electromagnetic electromagnetic frequencies respond to surfaces and what they travel through to and reflect off of or absorb by. Understanding that, along with understanding the technology that you can use to monitor that, allows you to infer quite a lot and to figure out a lot of, if you will, the mysteries of the environment, the weather. Every day we become more apt at predicting the weather. We've always been pretty good at predicting it about 5 minutes out. When I was a little boy, when the sky got dark and you heard thunder off in the distance, my grandmother would always say it's going to rain. And she was right probably 95% of the time. Now, she wasn't a meteorologist, but based on the available information, she could accurately predict it at a high level in a short timeline. The more information like this we have, the more capable our meteorologists are at predicting models and understanding how interactions work so that they can forecast more accurately at longer distances. Of course, as you all well know, there's still ample opportunity to get things wrong, and part of that is perhaps some of the confliction that some people and some scientists have over climate change data because of the wild variability that we see in weather patterns. It's just really hard to wrap your head around sometimes the idea that things are definitively getting warmer. But the data does show that. I don't think anyone who takes a really honest look at the data can argue the fact that we're not experiencing climate change and that global temperatures are increasing. I'm not necessarily going to hang my career on the cause of that, to say it's a single thing, but I would say that I'm of the opinion that it is probably a combination of multiple things, some and perhaps even many of which are directly related to human activities. And I think that we probably could do more to counteract it. I don't know if we could do enough to make a difference, but not doing anything clearly won't. And so this is one of those junctures between politics and science where all we can do as the scientists in the crowd is present the facts and some likely causes and some scenarios for what we think would happen if we tried to impact those results, and then leave it up to the politicians to decide how best to do what they want to do. Again, more photos from satellites of different things.